Welcome Math 8 mathematicians. Today we're going to be looking at one of our final proofs of 8th grade of the right triangle theorem. There are lots of other proofs out there, but we are not going to be looking at too many others right now, unless you bring them to me, in which case I would love to see what you come up with. But this is one of our final ones that we're going to look at in the class. This one is known as Bhaskara's right triangle theorem, or Bhaskara's proof to the right triangle theorem. Well, let's go ahead and get started. Before we actually look at who Bhaskara was, I want us to remind ourselves of what our objective is in this lesson. What are we really learning from this topic? Of course, I want you to be able to use and apply the right triangle theorem to understand a squared plus b squared equals c squared, to be able to use that as your mantra, spit it out at any time you need to. Apply it, find missing hypotenuses, hypotenuse, whichever one that word is. Find missing legs of a triangle, find distance between points. This is one of those ones that's a really applicable theorem. But in addition, there is also this idea that is our learning objective today, is that we are learning the history and the arguments that define the right triangle theorem. History of math is really rich and is really interesting because math is not discovered in a vacuum. It comes from building off of other ideas, from sharing between cultures, in some cases stealing from other cultures. Depends if you give credit where credit is due. And it's because that history of math is really showing how civilizations have developed and what their understanding of math is. There are lots of different concepts that were discovered independently in many civilizations and cultures around the world. There are a lot of things that were different that people discovered based on what their lifestyle was like and what they had fascination with. And then the most important thing I feel is really understanding, starting to develop in our heads how we develop these arguments that define not just the right triangle theorem, but define our knowledge of math. That's part of what we say when we say math is all about sense making. It's about argument making. It's about knowing what you know is true because there's no other way it could be. There are some assumptions we make. But this is the place where we start sort of pulling you to say, okay, this is no longer because Mixfox told you so. Don't believe them. You don't have to do that anymore. This is not first grade where you say 2 times 3 is 6, just believe it, just say it, come on. No. At this point, you're allowed to make arguments. This is a major pillar of what mathematics is. It's a growing field of mathematics. And it's really that fascination that has pulled so many cultures to it, is this understanding, or not this understanding, but this exploration into why do we know what we know? How do we know it's true? It's also one of the reasons that it's been seen as a holy field of study in so many different cultures is because it's really the uncovering of truth as we go through. So that argument piece of it, that's what proofs are all about. They're about convincing yourself, about convincing others why we know what is true is true. Yes, I know I'm opening myself up to lots of different questions, but you know what? You are mathematicians and you are allowed to ask them at this point. You don't have to believe me anymore. Don't ever let me say because I said so. At this point, you need to hear the arguments. You need to hear that developed sense-making. Let's start developing that part of ourselves. So, let's take a quick look at who Bhaskara was. This is a depiction of Bhaskara, also known as Bhaskaracharya. There was Bhaskara the first. This is Bhaskara the second. Oh, a little string mark there. We'll get there. I'll pull myself down so you can read this. So he was in India, born in 1114, died in 1185. Common era now, so this is now several hundred years after Pythagoras. Almost, 700, 600 years after Pythagoras passed away. So we are now hundreds of years later, centuries of years later, and he still comes up with a new and a very interesting right triangle theorem proof. So he was known for his proof of the right triangle theorem. It's a kind of fun one. But he was also known for a lot of other discoveries. He was a scholar, of course, a mathematician, a scientist, an astronomer, and a philosopher. One of those other discoveries you may have heard about, something that we call now gravity. He was one of the first people who proposed gravity existed. This is 500 years before Sir Isaac Newton proposed gravity and really fleshed out what that meant for us. But Bhaskara was one of the first people who actually said, there's something pulling things back down. He also looked at how we solve equations with integer solutions. This is the same thing that we saw in those original tablets from the Iraq desert. that we saw that there are these integer solutions, also now known as Pythagorean triples or Pythagorean triplets, like 3, 4, 5 triangles. Those are solutions to a squared plus b squared equals c squared. So he found a lot of those integer solutions. Of course, there are infinitely many solutions to this, both the integers, but also we see a lot of irrationals, so decimal solutions. But he really focused on just integers, those whole numbers that make it true. Another thing that he really looked at, speaking of developing arguments and not letting me say because I said so, he also really laid the foundation for how we think about dividing by 0. It's one of those things that you try to divide by 0 and Mr. BR looms over you and is like, you can't do that. And then you should come back and say, why not? Prove it. Then you've got him, because guess what? You can divide by 0. Yes, it's considered undefined, but it depends how you approach and what assumptions you make. So he was one of the first people who really thought about how could I make dividing by 0 work. And from that, he laid the foundation of what we now call the infinitesimal, the very, very, very infinitely small things, which also created this entire topic of calculus, of how do we make things get smaller and 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 continuing on forever and ever and ever until it's infinitely small. So he made a lot of great contributions from there. This is only a short list of what he did. We're going to jump right into his proof now. It should remind you of a proof that we saw called the classic 8th grader proof of the right triangle theorem. Notice I have a blue square. Hopefully it looks pretty squarish. And a green triangle, a right triangle inside that. I'm going to define, it's a right triangle right there. However, what I've done is I've just shifted it 45 degrees. But otherwise, it should look very similar to another proof. And we're going to basically start this proof the same way we started the other one. This right triangle is a little bit different, because before I had the legs build up the sides of my square, and now the hypotenuse is the same length as the side of my square. But I'm going to start the same way by taking this triangle. I'm going to pull this out a little bit so I can rotate it easily. I'm going to rotate it, and I'm going to nestle it into each of, well, in this case, I'm going to align it with each of the sides of the square in here. Hopefully I can do this well. Okay, there we go. Getting closer. And then, unlike other proofs so far that we've seen, we've really been defining the area in different ways. This is still going to have us define area in different ways. So it's still what I would consider an area proof of this theorem. However, this one's kind of fun because we are going to kind of cut and paste pieces of our square together in order to compare those areas. So, here we go. Get in there. Beautiful. Alright, so now we have our big square. Let's go ahead and label the sides in here so we can keep track of everything. Just like before, we're going to consider that small side length A. So this is going to be A. You know that these are congruent right triangles because you saw me cut and paste them, first of all. But also because they all are right triangles with the same side length, with the same angles, that makes them congruent. Here we go. This one last A right here. Let's label B as the long leg length. So that's going to be all the way across. Notice that B, actually I'm going to leave it inside the triangle for lack of confusion. Notice that B is actually overlapping A in each case. That's a horrible looking B. Let's try that again. There we go. So I'm going to try to kind of keep them so you can see both the A and the B in here. And finally we have C, which I said is the side of the square or the hypotenuse of each of these triangles. So we are going to look at the area two ways. Before we do that, I do want us to notice there seems to be a little square appearing in here. What is this little dude? You should be able to convince yourself, hey, this is a little square. Let's go ahead and do so now. Notice that there are right angles all the way around it, which means that they make this a straight angle because B doesn't have a kink in it. It's just one side of a triangle. That means that all of these have to be right angles inside of here. Okay, so it has to be a rectangle. Let's find the side length of each of these. Notice that the side length, I'm going to put it in black. This guy. Hey. The whole length across was B, and then we're going to take off A. So this is just going to be B minus A. We can do it for each of the sides on here. You'll see the same thing. We know that B is the same length as A. Each of these sides is B minus A. So we have a rectangle where all of these sides are the same length. Ugh, That's called a square. Okay, so now we're going to start pulling this apart. We're going to start cutting and pasting, and I'm going to go ahead and I'm just going to copy this entire thing, otherwise it's a little easy to lose what you are actually dealing with on here. So let's put them side by each other. This is the one we're really going to play with over here. So here's our original, and what I'm going to do, I'm going to label these triangles real quick. It's green triangles 1, 2, 3, and 4. Let's start having fun. The first thing I'm going to do is I'm going to take that number 1 triangle. Let's get another color we can highlight it, and let's take this pinky color. Wow. I'm going to take this guy, and I'm actually going to cut him and put him right next to triangle 3. So let's go ahead and do that. Take him and put him right, put him right next to triangle 3. Notice how that's making now a little, gross, nice little rectangle down here. And I'm going to do the same thing. I'm going to move triangle 4 up to meet triangle, so now I have this guy here. I'm going to move triangle 4 to meet triangle 2. So I'm going to do this again. I'm going to try to take him, and hopefully I can pull everything along with me. Beautiful. Oh, close. Let's get those guys overlapping a little bit better so we can see this. All right. So now you can see, okay, well, I've actually taken off, I didn't want that color. Hold on, hold on. Okay. There we go. So I've taken off this kind of piece over here, and I've moved it down here. So that's actually going to be down there. I've just taken off that piece, and the same thing, I've taken off this piece down here and moved it over. So at this point, I'm going to get rid of my square because I think it's confusing at this point. Move those pieces. But notice I still have left my little yellow highlighted square in there. So at this point, it's time to look at how we find the area in 2 different ways. First one, area 1, or area method 1. We have a square. Its side is c. So its area is c times c, or c squared. Haha, done. This one, more fun. Haha. Area 2. We have 2 rectangles and a square to deal with. So let's take a look. First one, let me clean up in here just a little bit. I'm going to start getting rid of some of these extra pieces so we can really look at what we're dealing with. There we go. Let's look at, I'm going to highlight it now in blue. I'm going to look at this piece in here. So again, we know that it is, this length over here was b, or long leg, and its base over here is a, so that means that that area of this guy is going to be a times b, length times width is the area of a rectangle. Well, let's do it again for this one down here. Again, I'm seeing that the length, or the height is a, the length is b. Hey, that means that we're going to have the same one. Let's add them together. So another, a times b, and then the last part over here is the little square. We already found the side length of the square is b minus a, so this is going to be b minus a times b minus a, so let's put that in here, plus b minus a times b minus a. We've seen a way to multiply these out before. So first I'm going to say ab plus ab, that's just 2ab. 2ab. This one, we're going to build our little box over here. Remember, we can do something like this. This is length b, this is minus a, this is b, this is minus a. Let's go ahead and find our area model. B times b is b squared. B times negative a is negative ab. B times negative a is negative ab. Negative a times negative a is positive a squared. So all together I have, let's make sure we have b squared. And then we have minus AEB minus AB. And we have plus A squared. Okay, minus AB plus 2AB. All of these cancel out. 2AB minus AB. We're left with B squared plus A squared. Whoa, ho, ho! Well, well, well. And it looks like area 1 was C squared. Area 2 was B squared minus A squared. That means we've got A squared plus B squared is equal to c squared. Right triangle theorem strikes again. Thank you, Bhaskara. All right, so that is our final proof that we're going to look at 8th grade. Happy exploring.